Okay, now going to a machine learning models, I'm going to take from scikit-learn. I'm going to call first linear models, and I'm going to import my linear regression. Okay. And the other thing that we might want to do is from scikit-learn, I'm going to from imported tree, and I'm going to import a decision tree regressor. And there are 3 different modes that we're going to try here. And from scikit-learn, we're going to take also what is called ensemble, and I'm going to import my random forest regressor. Okay. So those are my 3 models that I'm going to run. And I mentioned also in the slides that scikit-learn has some additional pre-processing tools like data split, standardization, and metrics, and so on. And what I'm going to do is import some of those. And in fact, let me import from scikit-learn dot pre-processing. I'm going to import a standard scaler. And this is an important step to make sure that your data is normalized to a minimum and a maximum that is comparable. So as you can see here, oil volume goes from 117 to 900, but choke percentage is going from 2 to 16 or 41. It's completely different ranges of the data. So this standardization, this standard scaler allows to make sure that everything is set to a particular range of a minimum and a maximum based on the mean and the standard deviation of the data. Okay. And one thing that I'm going to do, I'm not going to explain much about this, but this is to make our lives easier. I'm going to use a pipeline and to put all the steps that we want to build into the model. The other thing, this is pre-processing of the data. Let's say this is importing ML models. This is importing pre-processing functionalities. And the other thing is we want to use some metrics to address to understand the quality of a model. So importing metrics. From the metrics, I can use scikit-learn again from scikit-learn dot metrics. I'm going to import things like the mean square error. See what's happening there? Mean square error. Let's import that for the time being. So we have our ML models, the pre-processing, and the model. Let's do one very quickly. And the one that we're going to do is, let's do, this is a pipe model. Is going to be equal to my pipeline. And what I want to do to the model, to the data. So in this case, I want to do 2 things. I want to do a standard scaler. And my standard scaler, sorry. So this is a standard scaler. Yep. And the second thing that I would like to do is a regressor. So we want to standardize the data, and then we want to do a regression with the data. And that regression can be, in this case, let's say that we're going to do for the first time a linear regression just a linear regression. I'm going to leave it to a default value. Okay. So this is my pipe model. And what I want to do is feed the data. So if I go into a fit, what I call fit, let me run this and show you the fit here. I want to provide the X and the Y. And for the X and the Y, we saw that we need to provide, in this case, the X train, because we're going to train with we're going to fit with the training data. And the Y is a Y train. So again, if we see it, remember that this is a X train. It's just the values that we want to use to predict the Y train, which actually, if I show you the Y train, Y train and dot head. I don't know if it dot head is applicable here, but let's see. Yeah, what you see here is that these are the bottom hole pressures that we want to predict on, exactly as I explained before. So we have, now we want to predict the bottom hole pressure based on these values. We want to fit a linear model, very simple model. And the linear model is the simplest model that you can have of a form, let's say, of the most simple way to, or the simplest way to produce a model, which is something like the type of bottom hole pressure, the bottom hole pressure is equal to an interception plus a x1 times, in this case, times, let's say, oil volume, plus x2 times water cut, plus x3, and you get the idea. This is the simplest model that I can build. So this is a linear model. Of course, the linear model can be a bit more complicated, but what we're trying to fit is these coefficients here. We're trying to guess what are the values of these coefficients, so I have the better predictor, in this case, the bottom hole pressure. Okay, so it's the simplest model, and this is what we're doing here. And the scalar is just normalizing the data, as I mentioned, just to make sure that everything is within a range of probably something, a mid value of 0 and a max value of 1 or 1 point something. So it's so we feed the model, and we run this, and then feed the model. So the model has been fed very quickly, and now we can do a prediction. So I'm going to do a bottom hole pressure prediction. This is my prediction with a linear model, very simple linear model. I'm using all the default values of a linear model. Of course, there are some information that you can put in here as well. But so this linear model, in order to do a prediction, I can do actually, let's first assess the quality of a model. And the way I'm going to assess the quality of a model is I'm going to make a prediction. And the prediction is going to be on the X test data. Okay. Okay, so now we have a bottom hole pressure. And remember that we have Y test. So the Y test that we split from here, we have it there. So if you remember at the beginning, we have Y has the real values of a bottom hole pressure. So coming back to a presentation, so the real values, I have a real values of a bottom hole pressure. I use a train, and now I'm going to use the test data to test the quality of a plot, the quality of information. So let's do it. In fact, let's call it this, this is on the test. And let's do it in 2 steps. And this is on the train data. And let's produce exactly the same plot that we have in the presentation. Okay, so we have those two. So PLT plot, a scatter plot of, let's plot first the train data versus the white train. See how that looks? That looks like a very nice model. I have some values here that are, if I some labels here, PLT dot, it doesn't matter. So let's, this is equivalent to what we have here. Okay, so we have some plots. And ideally, if this is linear, it means that we have a very good, R square. Now that is on the train data. Let's see how the test data looks like. So this is a test. And this is a test. Yeah, the test data, yeah, that's actually very good. And there are some couple of points that are going a bit outside. But I can also calculate the score. And I'm going to take, let's say, let's print the score. And this is the only time that I'm going to print the score, but let's say print. And I'm going to say there's a training accuracy. And I'm going to use F strings here. My training accuracy is going to be equal to the pipe. I'm going to use it. The pipe model dot score, and I can take my X underscore train, my Y underscore train. So that is the quality of the model. That is a super model. Even if with a linear model, we're having a great model. So obviously the challenge is to see if a model is predictive. First, on the training data, it's a great model. Even the most simple model, a linear model, is quite predictive. And then the test model, test model, actually, surprisingly, it's even better. Test accuracy. Okay. So now that we have that, we can try to apply that to the next well and see if we have similar quality. Okay. So for that, I'm going to do a function. I'm going to copy a function here. I have it already. So first, we know already how good it works for the well, but let's say I want to fit. Let me copy a function where I have everything nicely labeled. Okay, let's do this one. So we have for well names, for welling well names, I want to take the production data. And for the time being, what I want to produce is just the plot without the prediction. Okay. So this is a plot per well. Okay. Let's add some more stuff here so that we have subplots. Add here some facilities to make some subplots. Bear with me just a second. Okay. minus I. And let's enumerate this. Okay, let's put a counter here. So now we're going to iterate through all the wells, but I'm just making just a couple of plots here. That's not producing as I was expecting. And yes, of course, so this is a DF bread. Row I. Okay, so I still don't have the predictor. I want to. Yes, no, it should be fine. So I have a dates, the bottom hole pressure, and I should have the title should be the name of a well. Let's put the title, the name of a well. And I'm iterating through all the wells. I'm not quite sure why it's not plotting the other wells. I don't know if you see any issue here, but I'm trying to take the well name, filter the data frame, then I take the filter data frame. I'm not sure why this is not flying here. X to the X row, blah, blah, blah. Name, production, well name. That's fine. Okay.
Can you put the fig X inside the loop?
I doubt that is big reason. I doubt reason. No, that shouldn't be the trouble.
Was it because you changed the data frame prod to another name, or?
No, because the data frame prod is the original one. I'm just making a plot, initial plot, and let's bring here the size. Let's see here if this is working here. This is usually see the chip here. Yeah. Oh, PFD show. It should be outside. Yeah, that's true. There you go. Right. So we have the bottom hole pressure of the wells. These are the original ones. And what we would like to do is check the quality of the model. So the first model that we produced was the linear model. So let's take straight away and see how the linear model on the rest of the model, on the rest of the wells. We can see that these two wells, because of the R square, is super. The root mean error is so high, almost close to 1, almost perfect. These wells shouldn't have an issue, except for the chotings. Shouldn't have an issue. Yes. If I do like to do let's add for DF prod a BHP of my linear model. I'm gonna call it linear. Yeah, let's call it linear. This is going to be equal to my pipe model. And what we would like to predict only with the predictors. Only with the predictors. And now I can underline here. I can add a plot, and this is going to be the dates, and instead of bottom hole pressure, we want to take the bottom hole pressure of a linear model. Okay, so in here we are just making the prediction already, but for all the wells in one go, And now I'm iterating here to test to see how it looks. And let me add this color green to see it in a bit of in a different color. Boom, that didn't work. Okay, water code and GOR not indexed because I need to add the water code and the GOR to the original data as well, to the fprot. So let me add those, that one. We calculated water code and GOR. So yes, this one. Okay. So let's add that to the fprot. Input is okay, infinite or a value too large for float. And again, let's add the constraint of the okay, that's what I did. And in fact, I don't want to mess up with my dfprot. What I'm going to do is I'm going to call it df2. And I'm going to filter this. So let's use dfprot2 instead. Okay.
One more on the top, just with the water volume.
Sorry, yeah. LM didn't like BHP LM. BHP DevBread, BHP LM. BHP linear model, DFP prot. This is BFP prot as well. Oh, finally. So as we would expect, the first two wells are perfect because our R square is perfect. So let's see what happens with the other wells. So surprisingly, it's not that bad, isn't it? So the green continuous line is the actual linear model, and the blue dots are the original data, the real data. So probably should zoom a bit, but that doesn't look so bad for a linear model, actually.